Alright, we're good. Let's go get started with this MATH221 Midterm 1. So, to get started, we've got question 1. Evaluate the limit if it exists and justify your answer. If the limit does not exist, state whether it's infinity, minus infinity, or neither, and fully explain its behavior. You may not use L'Hopital's, and if you use a theorem, clearly state which theorem you're using. To get started with part A, we have, let's call it L, the limit as t approaches 5 of the square root of t plus 11 minus 4 all over t minus 5. So first thing worth doing is always try just plugging in the value, see what happens. So if we plug in 5, we get the square root of 5 plus 11 minus 4 all over 5 minus 5, which is just the square root of 16 minus 4 over 0. Square root of 16 is just 4. 4 minus 4 is 0, so we're left with 0 over 0. And this is one of our indeterminate forms. And in this case, you could use L'Hopital's. Obviously, you can't in this specific question. But that's actually not going to be the easiest way. So this rule isn't too problematic. What we're going to do instead is let's go ahead and take a look at the fraction within the limit. So we have the square root of t plus 11 minus 4 over t minus 5. And the way we're going to approach this is a method of simplifying this numerator, because it's the part with the radical that's being problematic. And what this is called is multiplying by the conjugate. It's something you probably learn in pre-cal, but you won't use it very often. So in case you forgot, all we're going to do is we're going to multiply by the exact same thing, but instead of a negative, we're going to swap it out for a positive. And then of course we have to make the top and the bottom of the fraction the same, so that in essence we're just multiplying by 1. What this is going to be equal to is, you can imagine foiling, these first two terms multiplied just gives us t plus 11. Now the square root of t plus 11 times 4 is going to be plus 4 square root t plus 11. Now we're on to this second term. We have minus 4 square root t plus 11. And then we subtract 16 at the very end. On the bottom, we're going to be left with t minus 5 times the square root of t plus 11 plus 4, just like that. On the top, these two terms are going to cancel, and after simplifying, we're going to be left with t minus 5. That's going to be over t minus 5 times the square root of t plus 11 plus 4, just like that. And we can cancel out these two terms. We're just going to be left with 1 over the square root of t plus 11 plus 4. So now let's go ahead and substitute that back into our limit L. So we have L is equal to the limit as t approaches 5 of 1 over square root t plus 11 plus 4. Now let's go ahead and substitute 5 in here. We get 1 over the square root of 5 plus 11 plus 4, which is 1 over square root 16 plus 4, which is just going to be 1 over 8. And that's our final answer. Moving on to part B, we have a one-sided limit this time, and that is the limit as x approaches, let's go ahead and write it out actually. The limit as x approaches 5 from the negative side of x plus 5 over the absolute value of x minus 5. So the way I like to approach one-sided limits is just by kind of making a table and looking at how this limit is, what it's tending towards, I suppose. So when we take a look at x, we're approaching 5 from the negative side. So that's going to look like, say we start at 4.9, and then we go to 4.99. And then we could continue on, but this should be enough to see the behavior. Now let's go ahead and look at x minus 5. So this is going to be 4.9 minus 5, well that's going to be minus 0.1, and then 4.99 minus 5 is going to be 0.01, just like that. Let's go ahead and look at the absolute value of these terms. This is going to be 0.1, this is going to be 0.01. Perfect. Alright, now let's go ahead and look at the numerator just a bit. So x plus 5, well this is going to be 9.9, then 9.99. Now last, let's go ahead and look at that full fraction. So we're going to have x plus 5 over the absolute value of x minus 5, just like that. So that's going to be 9.9 over 0.1, which is just 99. We're going to have 9.99 over 0.01, which is 999. And then you can pretty clearly see that this is going to keep going up and up. And of course, on your test, you could put more values if you wanted to be sure. But what this tells us is that the limit as x approaches 5 from the negative side of x plus 5 over the absolute value of x minus 5 is going to be equal to infinity, just like that. Alright, moving on to the next limit. We have the limit as x approaches 0 of tangent 4x over 6x. And now the first thing you're going to want to do as always is plug in the 0. Because we don't have too much space here, unfortunately, I'm going to need that space. But if you plug in 0 to tangent, we know that's just going to be 0. And of course on the bottom we're also going to get 0, so that's an indeterminate form. And here we would love to use L'Hopital's, but unfortunately it's not allowed, as stated up here. So what we're going to do is we're going to rearrange this fraction just a bit. So the first thing I'd like to do is turn this 6 on the bottom into a 4. The way we'll do that is by factoring out a 2/3. So we'll have 2/3 times the limit as x approaches 0 of tangent 4x over 4x, right? And you can imagine putting that 2/3 back in, it's going to turn that back into a 6. So we haven't changed the limit at all. Now the last thing I want to do is split the tangent into its sine and cosine parts. So we're going to have 2/3 times the limit as x approaches 0 of tangent is sine x, or sine theta I should say, because it's actually going to be 4x in this case, over 4x. And then I'm going to write the cosine over here, 1 over cosine x, 4x, sorry. Alright, and then right here, this is where this is going to actually be pretty tricky. If your professor has mentioned this, this limit before, the limit as x approaches 0 of sine theta over theta is equal to 0, you could probably use that in your test. But in case your professor hasn't, let's go ahead and prove that. Sorry, this should be 1, not 0. So let's go ahead and prove that this limit is going to be that. So the way we're going to do this is let's draw a unit circle really quick. We've got our unit circle right here, and what we're going to do is we're going to take a look at just an arc of this. So this is going to be theta, and we can drop a line down from the edge. I'll go ahead and erase this so it's a bit more clear. We're looking at this arc. Now we know that this has a hypotenuse of 1, so what that's going to tell us is that this bottom bit is going to be cosine of theta, and this opposite is going to be sine theta. I'm just trying to figure out where I want to write this. I think I'll do it up here. And now the next thing we're going to want to do is we're going to want to keep extending this, pretend that's straight, sorry, and we're going to drop this down here. And so now this bottom bit right here is of length 1. Oh, that's weird. And what this is going to tell us is we can use tangent to find this further length right here. So this is going to be tan theta, right? Because tangent is opposite over adjacent, and now we have that the adjacent is of length 1. So the tangent is just the opposite angle. Now what we want to do is we want to set up some inequalities. So the first thing, we have that this inner triangle is the smallest, and so the area of a triangle is 1/2 base times height. So that is just going to be 1/2 cosine theta sine theta. That is going to be smaller than this kind of piece of the circle within the middle. And we know that that is going to be some fraction of the full circle. The full circle is going to be pi r squared, but the radius is 1, so it's just going to be pi times the fraction of the circle that theta is, and that's just theta over 2 pi, right? And then that is going to be smaller than the big triangle, which is 1/2 tan theta. Alright, and so now let's go ahead and actually rewrite tan theta as sine theta over cosine theta. And what this is going to tell us is let's go ahead and divide everything by sine and also multiply everything by 2 at the exact same time. So this one on the left is just going to turn into cosine theta. This is going to be less than or equal to. These two pi's are going to cancel, and we're multiplying everything by 2, so that 2 is going to disappear, and we're also dividing by sine. I know that's a lot of steps, so feel free to write out more if you want. This is going to be theta over sine theta. This is going to be less than or equal to. We multiply by 2, divide by sine. This is 1 over cosine theta, just like this. All right, and now the last step is we want to turn this into sine theta over theta. So we're going to flip all the fractions, and of course in doing so, we're going to have to flip each of the inequalities. So this is going to give us that cosine theta is greater than or equal to sine theta over theta, which is greater than or equal to, that should be theta, there we go, 1 over cosine theta. In other words, this function in the middle is squeezed between these two functions on either side. So now, let's go ahead and say, we'll go ahead and write out the limits and then call the squeeze theorem. So the limit as x approaches 0 of cosine theta, I'm sorry, this should be theta approaches 0 because we're switching variables. Well, this is just going to be equal to 1, which is less than or equal to the limit as theta approaches 0 of sine theta over theta is less than or equal to the limit as theta approaches 0 of 1 over cosine theta, which of course is just 1. And so now, by squeeze theorem, this tells us that the limit as theta approaches 0 of sine theta over theta is just going to be equal to 1, just like that. So now we can go ahead and return to our limit up here. We have that the limit, we'll go ahead and draw a little implies arrow. The limit is going to be 2/3, and now we're looking at the limit as x approaches 0 of sine of 4x over 4x. Well, this is of the form we just showed, so this is going to just be 1. And then if we plug in 0 into 1 over cosine, well, that's just going to be 1 over cosine of 0, which is 1. So this is also going to be 1. And we are just left with 2/3, which is our final answer. So yeah, that's a tricky one. But again, if your professor has covered this in class, this limit, which is pretty common, you're probably good to just mention that, and you don't need to prove it all like this. All right, moving on to part D. For this problem, we need to compute the limit as x approaches -3 of f of x, where f of x is given by this piecewise function right here. So this can be a bit tricky. Remember, when we're looking at the limit, we're not actually looking at the value when x is equal to -3. So we're not going to be looking at this part. What we're going to want to do is we're going to want to look at the limit from the left side and the right side. So let's go ahead and do that. So the limit as x approaches -3 from the negative side of f of x, well, let's go ahead and look at our piecewise function. When we are less than -3, we're going to be looking at this first part. So this is just going to be the limit as x approaches 3 from the negative side of x squared minus 2. Go ahead and put that in parentheses, and we can just plug 3 into that. We're going to get 3 squared minus 2, which is just 9 minus 2, which is equal to 7. And now for the positive side, we're going to have the limit as x approaches 3 from the positive side of f of x. This is going to be equal to the limit as x approaches 3 from the positive side. Let's go ahead and look at this top bit right here. We are going to have minus x squared plus x plus 12 all over x plus 3. And right here, if we plug in 3, we're going to get minus 9 plus 3. No, I'm sorry. This should be a negative. That's not right. There we go. That didn't change the first one because we square it. Sorry about that. So we're going to get minus 9 minus 3 plus 12, which is going to be 0. And then on the bottom, we're also going to get a 0, which I can go ahead and write out. So this is going to be minus 3 squared minus 3 plus 12 all over minus 3 plus 3, which is minus 9 minus 3 plus 12 over 0, which is 0 over 0. So this is an indeterminate form, so this tells us we need to simplify. You could use L'Hopital's, but actually the simpler way to do this is going to be to just reduce our fraction here. So we have minus x squared plus 12 over x plus 3. And now let's go ahead and factor out a minus 1. We're going to get x squared minus x minus 12 all over x plus 3. And now if we look here, we need two numbers that multiply to minus 12 and add up to minus 1. And by just a bit of trial and error, you can probably see that that's going to be x plus 3 and x minus 4 all over x plus 3. And so now these two x plus 3's are going to cancel, and we're left with a minus x minus 4. So now let's go ahead and reevaluate this limit. So we have the limit as x approaches minus 3 from the positive side of what we now know to be, let's put some brackets around this, minus x minus 4. This is going to be equal to a minus 3 minus 4, which is going to be equal to a minus negative 7, which is just equal to 7. And now because these two limits match, we can say, therefore, the limit as x approaches minus 3 of f of x is going to be equal to 7. Now the important thing, as you notice, is this is actually not the value of f of x, right? There's going to be a whole discontinuity, and so the limit can be different than the actual value. All right, moving on to part E, we have the limit as x approaches 1 of x squared cosine pi over x. And now, as always, let's go ahead and just plug in 1, see what happens. We're going to get that this is equal to 1 times cosine of pi. And cosine of pi, if you think about the unit circle, is going to be just minus 1. So this is going to be 1 times minus 1, which is just minus 1. And that's it. All right, moving on to question 2. All right, so for this question, we want to sketch the graph of a function f of x with all of the given properties. So for 1, f has a jump discontinuity at x equals minus 2. The limit as x approaches minus 2 from the negative side is 1. F of 1 is 1. The limit as x approaches 1 is 3. And then as x approaches 4 from the negative side, we go to minus infinity. And as x approaches 4 from the positive side, we go to positive infinity. And then f of x is continuous at all other x values. So first things first, let's go ahead and put some tick marks down. So let's say we have minus 1, minus 2, minus 3, minus 4. And then we've got 1, 2, 3, 4, 5, just like that. Let's give some y ticks, 1, 2, 3, 4. And of course, we're still going to have to label all of the points as it mentions, but this will just help us. So let's go ahead and start with the first one. So f has a jump discontinuity at minus 2. So we're going to have something weird happening right around here. And then we have the limit as x approaches minus 2 from the negative side is 1. So let's go ahead and go to 1. We're going to have a jump discontinuity. And we know as we approach this, we are getting closer and closer to the value of 1. So that'll fulfill that requirement. And we have the jump discontinuity, but it doesn't really say anything about where we have to jump to. So let's go ahead and just throw it up here at 3. And now the next bit of information we have is that f of 1 is equal to 1. So let's go ahead and put a dot right there. And what else do we know about f of 1? Well, the limit as f of x approaches 1 is equal to 3. And so what that tells us is that from both sides, we're going to be approaching 3. So let's put a circle up here. And we can just connect this line because we don't have anything else that we know about this. Now the next bit is that as we approach 4 from the negative side, we go to minus infinity, and when we approach it from the positive side, we go to positive infinity. So that's going to be an asymptote at 4, just like this. And so what we can do is we know that the limit as we approach 1 is 3, so we'll start from here, and then we'll just go down because we're going to negative infinity. And then we can come out of this with an asymptote, just like this. And that should be all we need. Let's go ahead and label some key points. So this asymptote is at x is equal to 4. This is going to be the point 1, 1. This is the point 1, 3. This is the point minus 2, 3. This one could be different for you, of course. This is the point minus 2, 1. And I believe those are all the key points that we need to label. We have our jump discontinuity. We're approaching 1. F of 1 is 1, which is labeled down here. We have the limit labeled here. And then we have our clear minus infinity, infinity. And everything else is continuous as we drew it off. Perfect. And of course, your graph could look different than this as long as it meets all these requirements. So, moving on to question 3, we're going to have to compute the derivatives of the following functions, use any method, and do not simplify your answer. So, to get started, we have f of t is equal to t squared times tangent of 9t. And so because this is two functions multiplied, we're going to want to use the product rule, which I'll just write out over here. If we want to take the derivative of, let's say, let's not use f so it doesn't get confusing, of g of t times h of t, well, that's just going to be equal to, we can do the derivative of the first times the second plus the derivative of the second times the first. Let's go ahead and move this over so I don't run out of space. Times g of t, just like that. And so now let's look at these two parts. So the first part, if we take the derivative of t squared, well, that's just going to be 2t by the power rule. And then if we take the derivative of tangent of 9t, well, we're going to have to use the chain rule for that. So remember that the derivative with respect to u of tangent u is going to be equal to u prime secant squared u, right? And so in this case, we have that u is equal to 9t, which tells us that u prime is going to be equal to 9. So this tells us that this derivative is going to be 9 secant squared 9t, just like that. So now let's go ahead and plug this all in. We get that f prime of t is equal to the derivative of the first, which is 2t, times the second, plus the derivative of the second, which is going to be 9 secant squared 9t, times the first, which is t squared. We don't need to simplify, so that's going to be our final answer. I'll go ahead and box it all in. Moving on to part B. This one is going to be our quotient rule. So let's go ahead and write it out first. We have h of t is equal to cosine t plus 8 over t squared plus 1. So just as a reminder for the quotient rule, we have that the derivative, let's say with respect to t of, call it f of t over g of t, is going to be equal to the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared, just like this. So let's go ahead and look at each of these functions. So first off, the derivative with respect to t of cosine t plus 8, this is just going to be the derivative of cosine plus the derivative of 8. And we know that the derivative of cosine is minus sine of t, and the derivative of 8 is just 0. And now we have that the derivative of t squared plus 1, well, that's just going to be equal to 2t, like this. So now let's go ahead and look at h prime of t. Give plenty of space for this. this is going to be equal to the bottom function, t squared plus 1, times the derivative of the top function, which we have as minus sine t, minus the top function, which is cosine t plus 8, times the derivative of the bottom function, which is just 2t, like this. And I'll go ahead and draw my fraction bar. On the bottom, we're just going to square the bottom function. So t squared plus 1, square all of that, just like that. And that's our final answer. Moving on to part C. This is going to be a bit of u substitution, which we can tell because we have kind of a weird function inside of another function. So let's go ahead and write this out. We have g of t is equal to secant of 2 over t plus 1. So let's go ahead and write this all out. The first thing we know is that the derivative with, let's call it with respect to u, of secant u is going to be u prime secant u tan u. And from here, we want to look at u. So if we have u as 2 over t plus 1, what is the derivative with respect to t of 2 over t plus 1? And this is, of course, what we call u prime. And now, what we can do is we can imagine factoring out this 2, and we're just left with 1 over t plus 1, and that is just going to be equal to the, actually, let's go ahead and rewrite this a tiny bit. We'll call this derivative with respect to t of 2 times t plus 1 to the minus 1, which will hopefully help you see we can just use the power rule. So for this, we're going to bring down the minus 1, and we get minus 2, right, because we multiply it by 2, times t plus 1 to the minus 2. And of course, we're chain ruling, but the derivative of t plus 1 is just 1, so we don't get anything special there. And now we're ready to write out our full derivative. We get g prime of t is going to be equal to u prime, which we know is minus 2 times t plus 1 to the minus 2, times secant of u is 2 over t plus 1, times tangent of u, which again is 2 over t plus 1, just like that. And we can box our final answer. Now, moving on to part D, we have h of t is equal to sine of the square root of 3t squared plus 8t plus 6. So again, this is going to be kind of an ugly chain rule because we have a function, and actually a radical, within another function. So let's go ahead and just start with the chain. So we'll let u be equal to the square root, which I'm going to write as raising to the power of 1/2. So the square root of 3t squared plus 8t plus 6 to the 1/2. So now that we have that h of t is actually equal to sine of u, and what is the derivative with respect to u of sine u? That's just u prime cosine u. So now we just need to find u prime. And so to do that, we're still going to need to do one more u sub. So we're going to let v be equal to 3t squared plus 8t plus 6. And so now what is the derivative? Actually, let's write this out explicitly. U is now equal to v to the 1/2. So the derivative with respect to v of v to the 1/2 is just going to be bring down the 1/2 and then subtract 1 times v prime, like this. And this is, of course, what u prime is equal to. Go ahead and move this over just a bit so you have some space. And so now let's find v prime. Well, v prime is going to be done with respect to t, right? And so let's take the derivative with respect to t. This is v prime of 3t squared plus 8t plus 6, which is going to be equal to 6t plus 8 the derivative of 6 is just 0. So now we can kind of start going back up through the chain to write out h prime of t. So we can write h prime of t as u prime cosine of u. But now what do we know u prime is equal to? Well, u prime is equal to 1/2 v to the minus 1/2 times v prime times the cosine of what is u? Well, u is just going to be equal to, we have it right up here, the square root of 3t squared plus 8t plus 6. And now the last step is to substitute what we know v is. So h prime of t is equal to 1/2 times v is 3t squared plus 8t plus 6 to the minus 1/2 times v prime, which is 6t plus 8, times this cosine term, which is cosine of the square root of 3t squared plus 8t plus 6, just like that. And that is our final answer. So, a bit tricky. The key is to just keep all of your u substitutions or v substitutions as well in this case straight. And there's other ways to write this out. This is just the way I prefer. So, moving on to question 4. Alright, so for question 4, we have that f of x is 4 over x, and we need to use the limit definition of the derivative to compute f prime of 1. No credit will be given if you do not use the limit definition of the derivative. So, just as a quick reminder, the limit definition is that f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And I'm going to write this slightly differently, just to make these fractions work nicer in a second. We're going to rewrite this as the limit as delta x approaches 0 of 1 over delta x times f of x plus delta x minus f of x, just like this. And of course this is the exact same thing. I'm just pulling out this delta x because in a second we're going to have a lot of fractions. So let's go ahead and substitute in what we know f of x is. So f prime of x is going to be equal to the limit as delta x approaches 0 of 1 over delta x times f of x plus delta x is going to be 4 over x plus delta x, and then minus f of x is just 4 over x. Now, this is going to be equal to the limit as delta x approaches 0 of 1 over delta x times, let's go ahead and give a common denominator here in the middle. We're going to get 4x over x times x plus delta x minus, we're going to have 4 times x plus delta x over x times x delta x, x plus delta x, sorry, just like this. And now this is going to be equal to the limit as delta x approaches 0 of 1 over delta x times, up here on the top we're going to, let's go ahead and distribute. We're going to get 4x minus 4x minus 4 delta x, like this, right? We're distributing this 4, and we have to subtract both of those terms. And then on the bottom, we're going to get x times x plus delta x. Up here on the top, this 4x and this 4x are going to cancel, and we're just going to be left with the limit as delta x approaches 0 of 1 over delta x times minus 4 delta x, all of this over x times x plus delta x. And now at this point, this delta x and this delta x are going to cancel, and we're just going to be left with the limit as delta x approaches 0 of minus 4 over x times x plus delta x. And now subbing in that delta x is 0, we get that this is equal to minus 4 over x times x, or minus 4 over x squared, which is f prime. And of course, you can always double check these problems by taking the derivative the normal way, using the power rule. And now the last step is we want to find f prime of 1. So we'll just substitute in 1. We have that f prime of 1 is going to be equal to minus 4 over 1 squared, which of course is 1. So this is just equal to minus 4. And that is the answer to part A. Now for part B, we want to find the equation of the tangent line to the graph of f when x is equal to 1. So we already know the slope at x equals 1, which is what we just found. So now we just need to find the y value. So let's find f of 1. This is going to be equal to 4 over 1, which is just equal to 4. So now we have a point and a slope. So let's use our point-slope form of the line, which is y minus y1 is equal to m, which is the slope, times x minus x1. In other words, we get that y minus 4 is equal to the slope, which we have as minus 4, times x minus 1. And now this should be an acceptable answer. It doesn't specify what form it wants the line in, but I'll go ahead and simplify it just in case. We get y minus 4 is equal to minus 4x plus 4, which gives us y is equal to, sorry, this should be an x here, minus 4x plus 8, just like this. And this is our final answer. Now we can move on to question number 5. Does the function f of x equals 8x to the 5th minus cosine pi x have a root on the interval 0 to 1? Explain why or why not, and if you use a theorem, clearly state which theorem you're using and why it applies. So, for this problem, we have that f of x is equal to 8x to the 5th minus cosine pi x, and we want to find if it has a root, or in other words, is it equal to 0 on the interval 0 to 1? So the first thing we might as well check is what do both of these endpoints look like? Because a lot of the times the endpoints can tell us what the function's going to look like. So let's go ahead and check out f of 0. Well, this is just going to be equal to 8 times 0 to the 5th, which is just 0, minus cosine of 0 times pi is just 0. Well, this is going to be 0 minus cosine of 0 is 1. So this gives us minus 1. And then f of 1 is going to be equal to 8 times 1 to the 5th minus cosine of pi. And of course, we get 1 to the 5th is just 1. So we get 8 minus cosine of pi is minus 1. So we get minus a minus 1, which gives us 9. And now what we see here is that on the left side of the endpoint, we're negative, and on the right endpoint, we are positive. Sorry, I should say the left endpoint. So what this allows us to do is we're going to be able to use the intermediate value theorem. So we can say by the intermediate value theorem, because f of x is continuous, which we know because polynomial functions are continuous and trigonometric functions, or cosine at least I should say, is continuous. So we know that the subtraction or addition of two continuous functions is going to be continuous. So because f of x is continuous and f of 0 is equal to minus 1 and f of 1 is equal to 9, there must exist a c somewhere between 0 and 1 such that f of c is equal to 0, because 0 is between 1 and 9. Or you could of course say because it's between f of 0 and f of 1. And that should be plenty, honestly, more than you need to write for your exam. Alright, moving on to question 6. We have that the position of a particle, there we go, is given by s of t is equal to 1 over t plus 1 plus 3t squared. So the first bit, we want to find the velocity of the particle. So the key to remember here is that the velocity is just the first derivative of the position. So if we have that s of t is equal to 1 over t plus 1 plus 3t squared, well, the velocity function is just going to be given by s prime of t. So we want to find the derivative of this function. And of course, we can just look at the derivative of each little section, because derivatives, if you are adding two functions, you can just take the derivative of each function and add them together. So let's first look at the derivative of t plus 1 to the minus 1, right, or 1 over t plus 1. Well, this is just going to be equal to, bring the minus 1 down, t plus 1, and then to the minus 2. And of course, again, like one of our previous problems, we are implicitly chain ruling, but the derivative of t plus 1 is just 1, so it's not going to affect anything. And then, of course, the derivative with respect to t of 3t squared, well, that's just going to be equal to 6t, like that. And so what we'll get is we'll get that v of t, which is equal to s prime of t, is going to be equal to minus 1 over t plus 1 squared plus 6t. And that's it. Go ahead, box everything, may as well. And now we want to find the acceleration of the particle. And the acceleration of t, with respect to t, is just going to be the derivative of v of t, like this. So, reminder that v of t is equal to, I'll go ahead and write it out as minus t plus 1 to the minus 2 plus 6t. And now we want to take the derivative of each of these parts. So the derivative with respect to t of minus t plus 1 to the minus 2, well, this is going to be equal to, bring that minus 2 down, and this minus 2 times minus 1 turns into a positive 2 times t plus 1 to the minus 3. And of course, the derivative with respect to t of 6t is just going to turn into 6, like this. So what we're going to be left with is that the acceleration function, which is the derivative of the velocity function, is going to be equal to 2 over t plus 1 cubed plus 6. And of course, you could write this this fraction right here as the to the power of the negative exponent. Either way will be perfectly valid, and this is going to be our final answer. Now moving on to question 7, we want to consider the function g of x is equal to this piecewise function right here. And now the first step is we want to see, is the function continuous at x is equal to 2? Make sure to justify our answer. Be careful to use the correct limit notation. So the way we can say a function is continuous is if the limit is equal to the value itself. So we want to show that the limit as x approaches 2 of, no, not f of x, sorry, of g of x is equal to the value of g of x. And because we have g of x defined on one of these sides, what we're really going to have to show is that the limit as x approaches 2 from the negative side is equal to the limit as x approaches 2 from the positive side. And if we can show this, then our function is going to be continuous. So let's first take a look at the limit as x approaches 2 from the positive side of g of x. And now this, of course, is just going to be equal to, we're going to look at this part, because this is the positive side, of 2 squared minus 3. This is going to be equal to 4 minus 3, which is 1. And we also have the limit as x approaches 2 from the negative side of g of x. Well, now we're going to be looking at this first piece right up here, and this is going to be equal to the absolute value of 2 minus 3, which is the absolute value of minus 1, which is just 1. And so now we can say, because the limit as x approaches 2 from the positive side of g of x is equal to the limit as x approaches 2 from the negative side of g of x. And of course this is still going to be equal to g of 2, right, because that is defined as the left-hand side of the limit. And these are all equal to the same value. We can say, I can't write, we can say g of x is continuous at x equals 2. And that is all we need to show for this one. Now we want to check, is the function differentiable at x equals 2? And again, make sure to justify our answer and be careful to use the correct limit notation. So what we're going to want to do is we're going to want to take a look at g prime of x. And so the way we'll do that is we'll look at the pieces from up above. So the derivative of the absolute value of x minus 3. Well, this is going to be tricky, except we can notice that this is only defined for x is less than 2. And this x minus 3 is always going to be negative when x is less than 2, right? The only way that this term here in the middle would be positive is if x was greater than 3. So we can actually rewrite this as minus x minus 3, because we're always going to have to be inverting it because x is less than 2, or we can rewrite this as 3 minus x. And so now when we take the derivative of this, well, it's just the derivative of 3 minus x, which is minus 1. And the derivative of x squared minus 3 is just going to be 2x by the power rule. And the first one is for x is less than or equal to 2. And the second one is for x is greater than 2, just like this. Yep, double check. And now what we want to do is we want to check the exact same things. Is the limit on the left side equal to the limit on the right side equal to the value itself? So let's take a look at the limit as x approaches 2 from the negative side of g prime of x. Well, this is going to just be equal to minus 1, because we're looking at x is approaching 2 from the negative side. And now let's take a look at the limit as x approaches 2 from the positive side of g prime of x. Well, this is going to be equal to 2 times 2, which is equal to 4. And so we can say, because the limit as x approaches 2 from the negative side of g prime of x is not equal to the limit as x approaches 2 from the positive side of g prime of x, the function g of x is not differentiable at x equals 2. At x equals 2. And that is all we have to write for that one. Alright, I think this is the final question. Yep. Final question, number 8. Clearly mark the correct answer for each of the following by completely filling in the appropriate bubble. No justification is needed. So, for this first one, we have, for the function f of x graph below, we have that the limit as x approaches 2 of f of x is equal to an L, which we have right over here. Given the value of epsilon marked in the graph, for which of these values delta is it true that if 0 is less than the absolute value of x minus 2, which is less than delta, then the absolute value of x minus L is less than epsilon. So basically what this question is asking is we want to find a delta that we can say add or subtract, so call this, so that's an 8. Call this plus delta and minus delta, that still stays within these bounds of the limit plus epsilon right here. And so what we can do is we can just look at these values that are given to us. So for the first one, if we have delta of 1.5, well, if we subtract 1.5 from 2, we're going to get 0.5, which is definitely outside of these bounds set by epsilon over here. For the next one, if we have delta of 1.3, well, if we add it, it'll just barely squeeze in over here, but if we subtract it, we're clearly going to get about 0.77, right? Which is not within these bounds, right? We want to keep these deltas within this line and this line right here. So the last value we need to check is 0.5. Well, if we subtract 0.5, we get 1.5, which is within this left bound right here. And if we add 0.5, we get 2.5, which is clearly within this right bound right here. So we know that delta equals 0.5 will satisfy this question. All right. For part B, we have that if f is a function such that the limit as x approaches a from the negative side is equal to the limit as x approaches a from the positive side, then f is continuous at x equals a. So you might initially want to say this is true, but it's actually going to be false, because let's say we have the limit approaches some value right here, and the limit approaches some value right here. Well, we could have a hole right here, right? We could have it kind of jump right here, and the limits are the same, but the actual value of f is not. So the way this would be true is if this was also equal to f of a, but because we don't have this, this must be false, because it's not always true. Next up, for part C, if f of x equals g of x over h of x, and h of 7 is equal to 0, then f of x must have a vertical asymptote at x equals 7. So now again, this one can be true sometimes, but let's imagine that g of x is also 0 at h of 7. So say h of x is something like x minus 7. Well, at 7, this is 0, but say on the top we also have x minus 7. Well, these two are going to cancel and give us 1. So we're going to have a hole, but not a vertical asymptote. So this is going to be false. All right. Next up, we have if h of x represents the number of people whose height is equal to x inches, the derivative is measured in inches per year. Well, so this isn't quite right, because what h of x is telling us a number of people with respect to inches. So the derivative is also going to be telling us something to do with the number of people. It's going to be the number of people as you change the amount of inches you're looking at. So because we don't see the amount of people here, we know that this is going to have to be false, because the derivative is going to keep the same units, just adding in the adjustment with respect to the dependent variable. And lastly, we have if f of 3 is equal to 2, then the limit as x approaches 3 of f of x is equal to 2. So again, this is sometimes true, but not always, right? Say we have f of 3 is equal to 2, it's way up here, but the limit is approaching something down here, there's a hole. We know that this is going to be false. And for these to be true, right, they have to always be true. And that is going to be all. So if you made it this far, nice job.